In part 1 of lecture 9, we'll answer the questions, what are quadruples and how are they generated? Semantic processing procedures need to create some form of intermediate representation of the program. We've already seen one such example, abstract syntax trees. Another such representation is called quadruples, or 3 address codes. Quadruples contain an assembly language level operator and 3 operands. And quadruples do not depend on any particular machine architecture. These instructions can include assignment, both for scalar values and array elements, the various arithmetic operations, both conditional and unconditional gotos, as well as the labels to which they transfer control, and identifying arguments and calling procedures. Quadruples consist of 4 fields, 1 operation, and up to 3 operands. Quadruples are also known as 3 address codes. Quadruples can be implemented using an enumerated type to represent the operations, and use pointers to symbol table entries to represent the operands. Here we see a sample program written in JSON. The name of the program is sample. The main program has 3 variables, the integer I, the real variables x and y. It has a procedure that will read 2 numbers, one an integer I and the other a real y. And you can see here it has those 2 instructions for it. The procedure then ends and the main program begins, calling the procedure, setting x equal to the sum of I plus y, and then writing x. Here we see our program sample represented in an abstract syntax tree. The root of the tree shows the program as a whole, which has 4 subtrees. Integer, which declares I as an integer. Real, which shows the declaration of x and y as real values. Procedure for the procedure readnums, the 2 declarations for integer and real, and also under the begin, the 2 executable statements. We then have lastly begin with the call to the procedure, setting the value of x equal to I and y, and then writing the result. Here you see the program quadruples. On the left, the main program, where we start by identifying I and y as the actual parameters for the procedure readnums. Below that, we call readnums, and then we set t1 equal to the float of I. We can't directly add an integer and a real, so we will use this function available only to the compiler to convert it to the equivalent real value. We then can do the addition. We then save the value in the variable x. t1 and t2 are temporary variables created by the compiler. We now identify x as the actual parameter for the method write, and then we return. On the right, you see the procedure readnums. We recognize I and y as the formal parameters. We now pass the value I, or prepare to pass the value I, to read, and the same thing for y afterwards, in both cases calling read. We'll start by looking at how we generate quadruples for an assignment statement. In this particular case, we have set z equal to a times x plus b times y. What we will do in this instance is that we will go to the right subtree of the assignment operator, and we will go through this in a post-order traversal. In this regard, we will find that t sub 1 is set equal to a times x, t2 is set equal to b times y, and then we do the addition to get t3 is set equal to t1 plus t2, and lastly, we will set z equal to t3. It might be better, at least in appearances, for us to set z directly equal to t1 plus t2. That complicates the translation process, and we will end up fixing it easily during optimization. Here we will look to translate the statement: if x is greater than y, then set z equal to x, else set z equal to y, and if. This is obviously what we're doing is setting z to the greater of the two values. Now, in this case, what we will look to do is that in the event that the opposite of the condition is true, we will jump further down. And when the condition that we actually have here in the statement is true, we'll fall through the statement below. Afterwards, we have to jump around where we are going to have the else case executed. That's why you see L2. We'll now have L1, z equals set y, and L2. This is something that we will look to do in every instance when we are looking at a structure like this. We can see that if there is no else case, translating an if statement becomes simpler. If y is greater than 0, then set z equal to x divided by y. And you can see here the two children that we have. If the opposite of the condition is true, we fall through to a label further down. And the various statements that we will do within the then clause of the if statement are executed here. Finally, again, the label that we jump around to if the condition were false, or the opposite of the condition is true. We're looking to generate quadruples for a while loop, and we'll look at the statement: while x is greater than 0, do set x equal to x divided by 2.0 end while. What we need first is a label here to indicate where we're going to come back. Each and every time as we begin the loop, we will have an if statement. If the opposite of the condition is true, or otherwise said, the condition itself is false, we will jump beyond the end of the loop. That not being the case, we'll execute whatever statements there are in the loop. In this case, just the one, x is set equal to x divided by 2.0. Then we'll go back up to the loop. If by any chance the expressions that we are comparing in that condition are expressions and not single variables, we would have to evaluate those expressions before the if statement. The quadruples for calling a procedure is actually fairly straightforward. In this case, I need to use the arg statement to recognize as an actual parameter x and another one for y, and then I can call the procedure. Generating quadruples for the procedure is not quite as simple as that, but pretty close. The name of the procedure becomes a label, and immediately after that I need instruction, the param instruction, which will allow me to indicate that the formal parameters in this case are x and y. After that I can have whatever instructions I need, and I have to have return at the end. Inserting semantic actions in a recursive descent parser is actually fairly straightforward. Here you can see the beginning of the procedure that we wrote to process or parse the header for the program. Now we're ready to install the data type for the identifier that serves as the program's name. We have tab index, which is going to give us the index in the attribute table for the name of the program. We'll set its semantic type as program and its data type as program. Below this, we will now initialize the record for this particular procedure, indicating the main program, so we know that any variables here belong to the scope of the main program. Here we are looking to process an expression, to parse it, and to generate intermediate code for it. Up1, up2, and up3 are structures holding the addresses of the three operands. An optor is an enumeration representing the operator, which will be plus or minus. We first process the term, and this will be stored as up 1. The rest of expression will give us the operator and the second operand. In this particular situation, up 3 is going to hold the result of the operation. The operation possibly might be null. If it isn't null, we're going to generate an arithmetic quadruple using the method that you see here. If the operator is null, then we'll simply assign it the value of up 1, and in either case, we will return up 3.